Okay, AP Chemistry, this is part 2. And again, all I'm doing is examples. This is solution stoichiometry of a precipitate reaction or a neutralization reaction. You've already watched part 1, which was the first 3 examples, and this is going to be example number 4 and number 5. Also want you to know that I'm actually going to do it in millimoles. Please remember that molarity is either moles of solute over liters of solution or millimoles of solute over milliliters of solution. The first 3 examples I did it in plain old moles per liter. The next couple of examples I'm going to do it millimoles per milliliter. And there are 2 advantages to doing it in millimoles per milliliter. Advantage number 1 is that they give you the volume in milliliters. You don't have to convert to liters. Advantage number 2, millimoles per milliliters gives you aesthetically pleasing numbers. Relatively large. You'll be dealing with 2.37 instead of 0.00237. So here's example number 4. 1250 mils of lead nitrate reacted with 2000 mils of sodium sulfate. We are going to do exactly the same thing as we did in the previous examples. Obviously a precipitate reaction, otherwise they're not asking for the theoretical yield of a precipitate reaction if it's not a precipitate reaction. So we are going to find the mass of precipitate formed, the identity of the precipitate formed, and then we are going to find the concentration of all the species in the mixture. So pretty much the same way. I am going to do this in millimoles. And just so you remember again, the number of millimoles will be calculated by taking the molarity and multiplying it by the volume in milliliters. First thing I'm going to do is I'm going to write the correct formula of my 2 reactants. It said lead 2 nitrate is reacted with sodium sulfate. Lead is a transition metal, so the Roman numeral tells you what charge on the transition metal. This is a double replacement reaction, so I'm going to write the products with the appropriate formulas. Lead sulfate forms and sodium nitrate forms from solubility rules. I know this is my aqueous. From solubility rules, sulfates are soluble except for group 2A, silver, mercury, and lead, and since this is lead, it is not soluble, so it is a solid. Balance it. All I need to balance it is a 2 here. It's balanced. Now for the information before a reaction occurs, it tells me that I have, and I'm doing this in millimoles, 1250 of a 0.05 molar solution and 2000 of a 0.025 solution. So what it tells me then is I have 62.5 millimoles of the compound. And I have 50 millimoles of this compound. Now again, these 2 are soluble salts, so technically speaking that's a misnomer. The compound doesn't exist in solution. So why do we need to know the number of moles of compound? The number of moles of compound will relate to the number of moles of each ion that makes up the compound. So for example, 1 lead in this lead nitrate, therefore I have 62.5 millimoles of the lead ion. And I have 125 millimoles of the nitrate because it's a 2 nitrates for every 1 compound. For the sodium sulfate, I have 100 millimoles of the sodium ion, because it's a 2 sodiums for every 1 compound, and I have 50 millimoles of the sulfate. And I'm actually going to do just a little side trip here that I did not do in the other ones. My net ionic equation is what I'm going to write down. And what I want you to notice from the net ionic equation is that the coefficients of the ions that make up the compound really do not change from the molecular equation that I originally wrote. So when I do the stoichiometry, while I understand that I'm doing it in compounds, it's going to be the same coefficients. So I'm actually going to use the net ionic equation here to do this limiting excess problem, but I'd get the same answer if I used the molecular. So first off, it's a limiting excess, and I have 62.5 millimoles of the lead, because it is part of the solid, and I have 50.0 millimoles of the sulfate, because it's part of the solid also. That leaves my nitrate, and I'm going to circle it, and my sodium as spectator ions. And I want you to realize that before the reaction, before mixing the 2 solutions together, I have 125 millimoles of nitrate and 100 millimoles of sodium. After the reaction, I'm still going to have the same number of moles, but a different volume. These 2 spectator ions do absolutely nothing but continue to float around in the solution, relatively useless. So with the 2 ions that make up the solid, I am going to figure out which one of them is my limiting and which one is my excess. And you'll notice that my stoichiometry in moles of or millimoles of, it's the same coefficients. Alright, so this one is very visual, but I'm going through the steps anyway. If I look at the 2 numbers, I find that this is the least amount of product, that means this is my limiting and this is my excess. Okay. Now, theoretical yield. Concerning the theoretical yield, my theoretical yield of precipitate. $50 millimoles. Now, how you do this is really up to you. 50 millimoles of the lead sulfate, and molar mass is going to be 303.30 milligrams for every 1 millimole, which gives you theoretical yield in milligrams with 3 sig figs will be 15,200 milligrams. Go ahead and divide that by 1,000 and it turns out to be 15.2 grams of precipitate. Next step, focusing on the excess ion, which according to our work is lead. From the net ionic equation, I am going to calculate how much lead ions I used to make the least amount of product. And the least amount of product is, of course, the 50 millimoles. Don't forget, the sulfate's used up. All those ions are gone. I do stoichiometry because I've got my 50 millimoles of the product, the precipitate. It's a 1-to-1 ratio. For every 1 mole of product, I need 1 mole of lead ions. Which kind of makes sense if you think about it. I used 50 millimoles of the lead ion to make the 50 millimoles of the precipitate. Second step, how much lead ions are left over? Well, I had, well, I'm going to go back, 62.5 millimoles of lead. So I had 62.5 millimoles of the lead ion originally before mixing. I used 50 of them to make my precipitate, my 15 grams. That leaves 12.5 millimoles of the lead ion left over. While I have this staring me in the face, I am going to calculate the concentration of the lead ions in the mixture using the additive volume. So I have 12.5 millimoles of lead in a total volume after adding it together of 3,250 milliliters, and that gives me a concentration of in 3 sig figs. The sulfate one is nice and simple because it's gone. The spectator ions, who are my spectator ions? My spectator ions are 125 millimoles of nitrate and 100 millimoles of sodium. So 125 millimoles of the nitrate over the same volume, because they're in the same volume, they're just not doing anything. And the sodium ion was 100 millimoles in the 3,250 milliliters, and I get for my nitrate 0.0385 molar, and for my sodium 0.0308 molar. Here's example number 5. 28 mils of a 0.25 molar nitric acid titrated with 53 mils of a 0.320 molar potassium hydroxide. And I know right off the bat this is a neutralization reaction, so we are going to figure out how much water is formed. and the concentration of the excess ion after the reaction goes to completion. So the first thing I'm going to do is write out the reaction. Nitric acid is an oxyacid. Potassium hydroxide is a strong base. Both of them strong electrolytes. This is a double replacement reaction. I get potassium nitrate and, which of course is H2O. This should be written a little different, sorry, oops. So this is not a precipitate, neutralization, awesome. My net ionic equation. Nitric acid is a strong electrolyte. The nitrate is a spectator ion. Potassium hydroxide is a strong electrolyte. The potassium is a spectator ion. You will notice that the coefficients for the molecular and the net are exactly the same. I have 28 mils of a 0.25 molar nitric acid, so I have 7.00 millimoles of the nitric acid. There's only one hydrogen ion per compound, therefore I also have 7.00 millimoles of the hydrogen ion. I have 53 milliliters of a 0.32 molar potassium hydroxide, so I have 17 millimoles of the potassium hydroxide, meaning that I have 17 millimoles of the hydroxide, since it's a 1-to-1 ratio, one hydroxide per compound. If I do my limiting excess problem, and I'm going to write it out even though you should be able to see it visually, from the net ionic equation, it's a 1-to-1 ratio. Oops, sorry, getting ahead of myself. Obviously going to be the limiting. This is going to be my least amount, because this guy's going to make 17 based on the stoichiometry. This is my least amount of product, my least amount of water, therefore this is my limiting, and this is my excess. So I have theoretically produced seven millimoles of water. And 7 millimoles of water converted from millimoles to mass is going to be 126 milligrams divided by 1,000, that should be 0.126 grams of water is produced. Focusing on my excess ion, which is the hydroxide, I am going to figure out again how many millimoles of hydroxide used to make the 7 millimoles of water. And I'm really not going to do the stoichiometry of it. I mean, it's pretty obvious it's a 1-to-1 ratio. For every 1 millimole of water, you use 1 millimole of hydroxide. This is a strong acid, strong base titration. So I've used, and I did just do the stoichiometry of it, didn't I? This is what I used. I had 17. I used 7. And that leaves 10. So the concentration of the hydroxide is going to be 10 millimoles over a total volume of 81. And that gives me 0.210. My hydrogen's nice and simple, gone. My nitrate, which is a spectator ion, the number of moles of nitrate gonna be 7 also. So 7 millimoles in 81 milliliters. So nitrate comes out to be nitrate comes out to be 0.0864 molar. And I think I have a typo. This is actually wrong. 10 divided by 81 is going to be 0.123. Sorry. Let's see. I think it's the potassium ion that's going to be the 210. 17.0, 81.0. Yeah, that's the 210. Sorry about that. But the good news is that's it.